Today we're looking at kinetic energy, being energy in motion. Remember, energy in general is anything that can produce change. So if something is moving, it has the potential to do some work on something else, to produce some change. So kinetic energy, we're going to see, is equal to KE1 is equal to 1/2 mv squared. Let's take a look real quick at where this comes from and also where this work kinetic energy relationship is. So if we go back to the definition of work, work is equal to force times distance. And from Newton's second law, again, that we know that force is equal to mass times acceleration. So again, we're back at that work is maddening homonym there. So if we take a look at this AD part, we can pull out what that reminds us from old linear motion equations, where 2AD, first time we saw that term, is equal to 1/2, VF squared, VF squared minus VI squared. So if we substitute the 2AD, solve for that, so we have AD is equal to VF squared minus VI squared, all divided by 2, and substitute that into there, we really have the work kinetic energy theorem. So work then is equal to mass times VF squared minus VI squared, all divided by 2. And if we factor that out, distribute it, we end up with 1/2 m, so pulling that 1/2 out, times VF squared, and minus 1/2 mVI squared. So that, and it's the net work, really, because we're dealing with the net force here. So here we have the net work is equal to the kinetic energy final minus the kinetic energy initial. So we can write that down too. Kinetic energy final minus kinetic energy initial. And that is the work energy theorem right there. So that's the work energy theorem. Here is the kinetic energy. So those are the two things we really need to hold on to and then try to apply those concepts. So if we hop over to our next slide, rewrite our formulas, make sure we have our units set. Refresher, work in general is equal to force times distance. Remember, those need to be parallel to each other. Kinetic energy is energy in motion, which is 1/2 mv squared. And the work energy theorem says that the net work done will equal to the change, remember delta means change, of the kinetic energy, which we can write as the final kinetic energy minus the initial kinetic energy. And all of those units for work and energy energy units are in joules. Remember, m is mass and v is velocity. Okay, so let's see if we can now apply this to some example problems. So let's erase this and take a look at our first problem. So here we have a 6 kilogram bowling ball rolling down an alley at a speed of 2 meters per second. How fast, so that's what we're looking for, how fast must a different ball of mass of 3 grams move and have the same kinetic energy? So we have given, we have two different masses, so let's call it M1 is 6 kilograms. V1 is 2.5 meters per second. And then I'm going to make another little column here. M2 is 3 grams. V2 is what we are looking for. And we want both of these kinetic energies, kinetic energy 1 equaling kinetic energy 2. So let's see if we can work through this. We have to be careful here because these two units don't agree. So we want to be in kilograms, so let's convert this right away to kilograms so we don't forget. So remember that 3 grams, set your factor label up. Divide that by 1,000 grams in 1 kilogram. So we end up with 0.003 kilograms. Okay, so now if we can find kinetic energy 1, we can substitute that in for what kinetic energy 2 is and hopefully get to this V2. So we know kinetic energy is 1/2 mv squared. And actually I'm going to put the kinetic energy on this side and make my substitutions. Is 1/2 m is 6 kilograms times 2.5 meters per second squared. And if we calculate that, we should come up with 18.75 joules. Alright, so that's the kinetic energy of 1. So now we'll come up here and deal with kinetic energy 2. So 1/2 m2 v2 must equal kinetic energy 1. So I'm going to leave it in terms of variables and switch this around and come up with our answer here. So solving for, we want v2 all by itself. So I'm going to multiply through by 2 and divide by m. So we end up with v2 is equal to 2 times the kinetic energy, all divided by the mass. Don't forget that's squared. So to get rid of a square, we have to take the square root. So v2 is equal to the square root of 2ke over m. And now we make our substitutions. 2 times the 18.75, all divided by the mass of 0.003 kilograms. And that V2 then comes out to 111.8 meters per second. There we are. Okay, so here's basic kinetic energy formula. Oftentimes we're looking for a mass or we're looking for a velocity, knowing how much energy it has. So we just have to switch this around. So we need to make sure we have those algebra skills to switch around to find that velocity. Okay, let's start the next problem, next example, and see how we do with that. I'm going to let you guys finish this one. So we'll get things set up and then see what you can do with it. So here we're going to look, we have a 60 kilogram baseball player, runs towards home plate at the speed of 6 meters per second and slides to a stop. If the coefficient of friction between the player and the ground is 0.4, how far does he slide? So here we have a mass of 60 kilograms. He's traveling at a speed initial of 6 meters per second and a final speed of 0 because he comes to a stop. And the coefficient of friction, mu, is equal to 0.40. We're looking for distance. This one looks like it's kind of tricky, but if we draw this out, maybe it'll help. So here's my baseball player as just a dot. If we do a free body diagram, he has weight, he has a normal force, right? The ground pushing back up on him, and he comes to a stop because something must stop him, and that something is friction. He's not running forward anymore, so his velocity was going this way, but he's stopping, so velocity is not a force, so that's our free body diagram. And remember, pull back some other information. Remember, the force of friction is equal to mu times the normal force. So we have the mu. Normal force will equal to the weight, and remember the weight is mass times gravity. So if we take this a step further before I leave you to finish, go back to what we said, that the net work is equal to the kinetic energy final minus the kinetic energy initial. And that net work will be done because of the force of friction acting over a distance, and that will equal to the 1/2 mv final squared minus the 1/2 mv initial squared. Okay, see if you can take and cook this down some more and see what you come up with for a final solution.